Hi there, and a heartfelt welcome. I'm so happy you've joined me today. Before we dive in, I'd love it if you could share in the comments where in the world you're tuning in from and what time it happens to be for you right now. It's always so special to see our little community connecting across time zones. A gentle thank you as well to everyone who has already subscribed and shown love with likes on the videos. It truly makes a difference. And if you have ideas or topics you'd like me to cover, please let me know in the comments. With that, let's get started. Chapter 1. Understanding Supernovae and their types. In the vast expanse of the universe, where time and space converge in a celestial embrace, there exist phenomena so magnificent and powerful that they reshape our very understanding of existence. Among these awe-inspiring events are supernovae, the spectacular deaths of stars that mark the end of their life cycles and the birth of new cosmic wonders. A supernova is not just a bright flash of light in the night sky. It is a cataclysmic explosion that releases an unfathomable amount of energy, outshining entire galaxies for brief moments. The significance of supernova extends far beyond their visual grandeur. They play a crucial role in enriching the universe with heavy elements, contributing to the formation of new stars, planets, and even life itself. Understanding supernovae begins with recognizing their two main types, Type 1 and Type 2. Type 1 supernovae occur in binary star systems, where a white dwarf star accumulates matter from its companion until it reaches a critical mass. This triggers a runaway nuclear reaction, resulting in a brilliant explosion. Type 1 supernovae serve as vital cosmic markers, helping astronomers measure vast distances in the universe and providing insight into its expansion. In contrast, Type 2 supernovae arise from the dramatic collapse of massive stars, those with at least 8 times the mass of our Sun. When these stars exhaust their nuclear fuel, their cores succumb to gravity, imploding with immense force and ejecting their outer layers into space. The remnants of such explosions often leave behind neutron stars or black holes, enigmatic entities that continue to captivate the imagination. Imagine for a moment the life cycle of a massive star. Born from clouds of gas and dust, it embarks on a journey fueled by nuclear fusion, where hydrogen atoms fuse to create helium, generating the energy that makes the star shine. Over millions of years, this stellar furnace evolves, cycling through various stages as heavier elements form in its core. Once the star runs out of hydrogen, it begins to fuse helium into carbon and oxygen, continuing this process until it ultimately creates iron. Iron, unlike lighter elements, cannot release energy through fusion, leading to the star's eventual demise. What happens next is a breathtaking transformation. The core collapses, and in a rapid sequence of events, the outer layers are expelled, creating a spectacle that illuminates the cosmos. The mechanisms behind supernova explosions are as intricate as they are fascinating. In a Type 2 supernova, the core collapse occurs when the star's core reaches a critical density. As gravity compresses the core, temperatures soar, and a shockwave forms. This shockwave travels outward, pushing against the outer layers of the star, which are then expelled at tremendous speeds. The energy released during this process is staggering, equivalent to the total energy output of the Sun over its entire lifespan, all released in just a few weeks. The aftermath of a supernova explosion is a scene of both chaos and beauty. The ejected material enriches the surrounding interstellar medium with heavy elements, such as carbon, oxygen, and iron, essential building blocks for new stars and planets. It is in this cosmic recycling that we find our own connection to the universe. As the physicist Neil deGrasse Tyson eloquently stated, "The atoms in your body are traceable to stars that exploded and formed the elements." We are, quite literally, made of stardust, and supernovae are the crucibles in which these elements were forged. Supernovae also emit a spectacular array of light and radiation across the electromagnetic spectrum. From visible light to gamma rays, They serve as cosmic beacons that reveal the underlying mechanics of the universe. Observing these explosions allows astronomers to glean insights into the fundamental laws of physics, the expansion of the universe, and the nature of dark energy. Each supernova serves as a unique laboratory for scientific discovery, challenging our understanding and provoking new questions. Consider the cosmic significance of these events. When a supernova occurs in a distant galaxy, it not only illuminates the darkness, but also provides a snapshot of the universe at a specific moment in time. By studying the light curves and spectral lines of supernovae, astronomers can reconstruct the history of the universe, offering clues about its formation and evolution. The light from these explosions can travel for millions, even billions of years, reaching us as a testament to the dynamic processes that have shaped the cosmos. As we explore the profound implications of supernovae, we encounter the stories of remarkable individuals who have devoted their lives to understanding these cosmic phenomena. Among them is the late physicist Robert Kirshner, whose work on Type Ia supernovae was instrumental in revealing the accelerated expansion of the universe. Kirshner's research, combined with that of others, led to the groundbreaking discovery of dark energy, a mysterious force driving this expansion. His insights have forever changed our perception of the cosmos, illustrating the interconnectedness of supernovae and the larger fabric of the universe. Imagine standing under a starlit sky, gazing at the constellations, each star a distant sun, with the knowledge that many of these celestial bodies will one day meet a spectacular end. The vastness and complexity of the universe can be both humbling and exhilarating. The life and death of stars remind us of the cycles of existence and the beauty that emerges from destruction. The journey of understanding supernovae is not just a scientific endeavor, it is a quest for knowledge that delves into the very essence of our being. It beckons us to ponder our place in the universe and the stories written in the stars. What mysteries lie ahead, waiting to be uncovered? As we continue to explore the cosmos, the legacy of supernovae will undoubtedly guide our path, illuminating the dark corners of our understanding with their brilliant light. The aftermath of a supernova explosion is not merely a momentary spectacle, it heralds the birth of new cosmic structures and phenomena. As the supernova ejects its outer layers, these remnants expand into the surrounding space, forming nebulae that can give rise to new stars and planetary systems. Imagine the colorful clouds of gas and dust swirling in a cosmic ballet, where the remnants of a once mighty star serve as the cradle for future generations of stars. This process is known as stellar recycling, and it plays a crucial role in the evolution of galaxies. One of the most famous examples of this phenomenon is the Crab Nebula, the remnant of a supernova observed in the year 1054. This nebula, a stunning tapestry of colors and shapes, continues to inspire astronomers and laypeople alike. It is a vivid reminder of the life cycle of stars and serves as a laboratory for studying pulsars, highly magnetized, rotating neutron stars that emit beams of electromagnetic radiation. The pulsar at the center of the Crab Nebula spins rapidly, a lighthouse in the darkness of space, providing a unique opportunity to observe the effects of a supernova on its surrounding environment. Beyond the immediate aftermath, supernovae also have profound implications for the structure of the universe itself. They contribute to the chemical enrichment of galaxies, seeding the interstellar medium with heavy elements forged in the hearts of stars. This process is vital for the formation of rocky planets and, ultimately, the emergence of life. When we gaze at the stars, we are not simply looking at distant suns. We are witnessing the legacy of countless supernovae that have shaped the cosmos over billions of years. What would it be like to stand on a newly formed planet, surrounded by elements birthed from stellar explosions? The air thick with the remnants of supernovae, the ground rich with carbon, oxygen, and iron, all waiting to be woven into the fabric of life. Each breath could be a testament to the ancient stars that exploded to provide the very building blocks of existence. This connection between supernovae and the origins of life is a profound reminder of our place in the cosmos. The mechanisms of supernova explosions, though complex, reveal the intricate workings of nature. In Type 1 supernovae, the process begins when a white dwarf star accumulates matter from a companion star. As it reaches a critical mass, the pressure and temperature in the core soar. The resulting thermonuclear runaway leads to a catastrophic explosion, releasing a burst of energy that can outshine entire galaxies. This violent event is not a simple act of destruction. Rather, it initiates a series of processes that lead to the creation of new materials and cosmic structures. In contrast, the core collapse of a massive star in a Type 2 supernova is a dance of gravity and nuclear forces. Once the core's nuclear fuel is exhausted, gravity takes over, compressing the core to extraordinary densities. This collapse is so intense that it generates a shock wave, which then travels outward, ejecting the outer layers of the star at velocities that can reach several thousand kilometers per second. This process not only produces the brilliant flash of light that we observe, but also disperses the star's material into the surrounding space, enriching it with elements forged during its lifetime. As we reflect on the life cycles of these enormous stars, we can't help but feel a sense of wonder at the interconnectedness of the universe. The late astronomer Carl Sagan once noted, "The cosmos is within us. We are made of star stuff." This poetic insight captures the essence of our relationship with the cosmos, illustrating how the very elements that make up our bodies were once part of ancient stars that met their ultimate fate in a supernova explosion. The study of supernovae is not without its challenges. Observing these celestial events requires both patience and advanced technology. Telescopes equipped with sophisticated instruments can capture the light emitted by a supernova across a spectrum of wavelengths, revealing the elemental composition, velocity, and distance of the explosion. Each observation adds a piece to the puzzle of understanding the universe's expansion and the fundamental forces that govern it. Consider the Hubble Space Telescope, an extraordinary marvel of human ingenuity that has provided breathtaking images and invaluable data about supernovae. With its ability to peer deep into space, Hubble has allowed astronomers to witness the death throes of stars in distant galaxies, illuminating the history of the universe as it unfolds. Each image captured is a snapshot of evolution, a moment frozen in time that tells a story of creation and destruction. As we continue to unravel the mysteries of supernovae, we encounter a realm filled with questions yet to be answered. What secrets lie in the remnants of these explosions? How do they interact with the interstellar medium? The answers to these questions will not only deepen our understanding of supernovae, but also shed light on the very nature of the universe we inhabit. In this cosmic theater, supernovae serve as both endings and beginnings. They remind us that destruction is often intertwined with creation, a cycle that resonates through the ages. The light of a supernova can illuminate the darkest corners of our understanding, guiding us through the vastness of space and time. What wonders await us as we explore this celestial phenomenon further? Each inquiry opens a new door, inviting us to step into the unknown, where the legacy of supernovae continues to shape the narrative of our existence. Chapter 2. The role of supernovae in element formation. As we explore the cosmos, we find ourselves drawn to the extraordinary phenomenon of supernovae, which are not merely celestial fireworks but profound events that shape the very fabric of our universe. Within these cosmic explosions, a process known as nucleosynthesis unfolds, transforming lighter elements into heavier ones, thus enriching the universe with the building blocks of life. Nucleosynthesis during a supernova occurs under conditions of extreme temperature and pressure, creating a crucible for the formation of elements that constitute our world. In the final moments of a massive star's life, when the core collapses and the outer layers are ejected at incredible velocities, the temperatures soar to millions of degrees. This environment is ripe for nuclear reactions, where hydrogen fuses into helium, helium into carbon, and further into heavier elements like iron, nickel, and beyond. Imagine for a moment the chaos and brilliance of a supernova. As the star reaches the endpoint of its nuclear fusion journey, it can no longer support itself against gravitational collapse. The core implodes, triggering an explosive rebound that sends shock waves rippling outward. In these moments, elements are forged in the fiery heart of the explosion. Elements that will one day form planets, stars, and even the very atoms of our own bodies. The heavy elements created in these cataclysmic events are not confined to the remnants of the dying star. Instead, they are cast into the interstellar medium, a vast expanse of gas and dust that fills the spaces between stars. This distribution of heavy elements is essential for the cosmic cycle of matter. When a supernova explodes, it ejects an array of elements, from carbon to uranium, enriching the surrounding space with material that will be incorporated into future generations of stars and planets. As we consider the implications of this elemental dispersal, we ask ourselves, what happens next? How do these heavy elements influence the birth of new celestial bodies? The answer lies in the process of star formation, where clouds of gas and dust, now enriched by supernova remnants, collapse under their own gravity. As these clouds condense, they form protostars, which will eventually ignite nuclear fusion and become new stars. The presence of heavy elements increases the likelihood of forming rocky planets, like Earth, which are crucial for the development of life as we know it. The significance of supernovae extends far beyond their immediate explosive brilliance. They are vital players in the cosmic chemical evolution of the universe. The elements produced and distributed by these stellar explosions contribute to the creation of complex molecules, laying the groundwork for life. For instance, the carbon that forms the backbone of organic molecules finds its origins in these stellar deaths. As astrophysicist Neil deGrasse Tyson eloquently stated, "The atoms in your body are traceable to stars that exploded and scattered elements across the universe." This profound connection between supernovae and our very existence invites us to reflect on the interconnectedness of all things. Moreover, supernovae also play a crucial role in regulating star formation rates in galaxies. The shock waves generated by the explosion compress nearby gas clouds, potentially triggering the birth of new stars. This feedback mechanism is a delicate balancing act. While supernovae enrich the interstellar medium, they also influence the dynamics of star formation, shaping the evolutionary path of entire galaxies. Consider the Milky Way, our galactic home, where supernovae have peppered the cosmos with essential elements over billions of years. Each explosion has contributed to a complex web of stellar evolution, where the remnants of ancient stars become the seeds for new creation. The elements forged in these fiery events transform the very landscape of the universe, allowing for the diverse array of celestial bodies we observe today. As we gaze at the night sky, we are witnessing the legacy of these supernovae. Each twinkling star is a testament to the cycles of life and death in the universe, a reminder that we are all stardust, born from the remnants of ancient giants. The narrative of supernovae is not merely a tale of destruction, it is one of creation, an ongoing cycle that continues to shape the cosmos. The importance of supernovae in cosmic chemical evolution cannot be overstated. They are the cosmic forges where the elements we deem essential, oxygen, nitrogen, and iron, are born. These elements are fundamental to the formation of life-supporting planets and the very atmosphere we breathe. The aftermath of a supernova sets the stage for new worlds to emerge, worlds that may harbor life, just as Earth does. In contemplating the vast timescales involved, we can appreciate the grand narrative woven through the fabric of the universe. Stars live and die over millions of years, yet their deaths give rise to new beginnings. The remnants of one generation of stars become the building blocks for the next, in an endless cycle of birth, death, and rebirth. As we delve deeper into the mysteries of supernovae, we are reminded of the delicate balance that governs the universe. These fiery explosions are not just random events. They are pivotal moments that shape the chemical composition of the cosmos, influencing everything from the formation of stars to the emergence of life itself. Each supernova carries with it the potential for new beginnings, a reminder that even in destruction there exists the possibility of creation. The cosmic landscape is rich with stories of incredible phenomena, and supernovae serve as a beacon of transformation. They illuminate the pathways through which elements travel, connecting the past and future of our universe. As we continue our exploration of the cosmos, let us remain in awe of the intricate processes that govern our existence and the powerful supernovae that shape the world around us. The remnants of supernovae, often in the form of nebulae, become fertile grounds for new stars and planetary systems. These nebulae are vast clouds of gas and dust, rich with the heavy elements synthesized during the explosive death of their progenitor stars. As gravity draws these materials together, they begin to coalesce, forming dense regions that eventually ignite into new stellar bodies. The cycle of stellar life continues, driven by the very elements forged in the fiery crucible of supernovae. Imagine a vast, swirling nebula, its colors vibrant and alive, the remnants of a once mighty star illuminating the dark void. Within this cosmic nursery, the conditions are ripe for the birth of new stars. As parts of the nebula collapse under their own gravity, they gather into clumps that heat up, eventually reaching temperatures high enough to trigger nuclear fusion. This rebirth is not just a continuation of a singular star's life. It marks the beginning of a new generation, one that carries forward the legacy of its predecessors. How does this process of star formation relate to our own solar system? The material that formed the planets around our sun can trace its roots back to ancient supernovae. This connection underscores the symbiotic relationship between stellar death and creation. The heavy elements produced during supernovae are precisely what give rise to rocky planets, those that are capable of hosting life as we understand it. Without the explosive deaths of stars, our Earth, rich with the building blocks of biological complexity, may never have existed. Furthermore, the interplay between supernovae and the interstellar medium also plays a role in regulating the life cycle of galaxies. The shockwaves produced by supernovae can compress nearby gas and dust clouds, sparking the conditions necessary for star formation. This dynamic balancing act influences the rate at which stars are born, shaping the evolution of galaxies over billions of years. The Milky Way, our galactic home, is a prime example of this intricate process, where supernovae have played a pivotal role in the development of diverse stellar populations. As we ponder the profound impact of supernovae, we must also consider their role in the cosmic chemical evolution. The heavy elements released into the interstellar medium are essential for the formation of complex molecules, which are the precursors to life. Elements such as carbon, nitrogen, and oxygen, forged in the hearts of dying stars, combine to create the molecules that build the fabrics of biological systems. The cosmic dance of creation continues, linking the fates of stars, planets, and life itself. Reflecting on the words of renowned astrophysicist Carl Sagan, we are reminded that the cosmos is within us. We are made of star stuff. This statement encapsulates the essence of our connection to the universe. Each of us carries within our bodies the remnants of ancient stars, a tangible reminder of our place in the grand scheme of cosmic evolution. The journey of these elements does not end with the formation of new stars. Over time, as stars evolve, they continue to produce new elements through processes like stellar nucleosynthesis. When massive stars undergo their own life cycle, they contribute to the universe's elemental diversity. After their own explosive ends, they too will enrich the interstellar medium, perpetuating the cycle of star birth and death. This continuous exchange of material creates a rich tapestry of elements that populate galaxies, forming the basis for everything from the air we breathe to the intricate structures of DNA. Supernovae also serve as cosmic timekeepers, allowing astronomers to understand the age and evolution of galaxies. By studying the remnants of these explosive events, scientists glean insights into the history of our universe. Each supernova carries a story of its origin, the conditions of its explosion, and its aftermath, providing invaluable data for understanding the dynamics of cosmic evolution. In contemplating the impact of supernovae, one cannot overlook the beauty and complexity of the universe they help create. They remind us that destruction is often a precursor to creation, and that the end of one life can give rise to many others. The cycle of life and death among stars is mirrored in our own existence, inviting us to reflect on the interconnectedness of all things. As we continue our journey through the cosmos, let us embrace the wonder of supernovae and their pivotal role in shaping the fabric of the universe. Each explosion is a testament to the remarkable processes that govern our reality, reminding us of the delicate balance that sustains life and the intricate web of connections that bind us to the stars. The story of supernovae is ongoing, a vibrant narrative of transformation that resonates throughout the vast expanse of space. The universe, vast and enigmatic, continues to unfold its mysteries, with supernovae lighting the way as beacons of creation. They serve as reminders of the past while paving the path for the future, guiding the evolution of galaxies and the formation of new worlds. In every moment of awe we experience when gazing at the night sky, we are witnessing the legacy of these celestial explosions, a reminder that we are all intertwined in this grand cosmic journey. Chapter 3. Supernova as catalysts for star formation. As the remnants of a supernova drift through the vastness of space, they carry with them not only the heavy elements forged in their explosive death throes, but also the potential for new beginnings. The shock waves generated by these cataclysmic events resonate through the cosmos, stirring the fabric of molecular clouds and inspiring the birth of new stars. Picture the scene: a stellar graveyard, illuminated by the fading light of a once mighty star, now serving as a nursery for future celestial bodies. When a supernova occurs, it releases an immense amount of energy, producing shock waves that travel at staggering speeds. These shock waves compress surrounding gas and dust, igniting a cascade of processes that can lead to star formation. The force of a supernova can trigger the collapse of nearby molecular clouds, regions dense with gas and dust. As the shock waves propagate, they create fluctuations in density, regions where matter gathers and begins to coalesce under the influence of gravity. This is where the magic begins. Imagine a molecular cloud, initially calm and unassuming, suddenly disturbed by the powerful shock waves. The gas and dust within it begin to clump together, driven by gravitational attraction. As these clumps grow denser, they can reach a critical point where the pressure and temperature rise sufficiently for nuclear fusion to commence. This delicate balance of timing and conditions is crucial for starbirth. Too much turbulence or disruption, and the potential for star formation may be lost. Astrophysicists study these processes meticulously, seeking to understand the precise conditions that lead to the birth of stars. One of the key elements they explore is the role of turbulence within molecular clouds. Turbulent motions can create regions of varying density, and when these denser areas encounter the shock waves from a supernova, they may collapse to form new stars. It is a beautiful interplay of chaos and order, an orchestration of cosmic forces that leads to the creation of luminous bodies that will one day illuminate the cosmos. The timing of a supernova's explosion is equally critical. If a supernova occurs within a certain distance from a molecular cloud, the shock waves can stimulate star formation effectively. However, if the explosion happens too far away, or if the cloud is not dense enough to respond, the effect may be minimal. This delicate timing has led researchers to ponder: can we predict which supernovae will lead to new star formation? It is a question that has driven countless studies, revealing that the universe operates not just on chance, but on intricate connections between cosmic events. Consider the case studies of star formation in supernova remnants. One of the most notable examples is the Crab Nebula, the remnant of a supernova explosion that has become a rich laboratory for understanding how stars can be born from such cosmic devastation. The Crab Nebula, with its intricate filaments of gas and dust, is a vibrant tapestry of chaos, yet within this chaos lies the potential for new stars to ignite. Researchers have observed regions within the nebula where the conditions are ripe for star formation, revealing that even in the aftermath of destruction, life can flourish. Another stunning example comes from the stellar nursery known as the Pillars of Creation, located in the Eagle Nebula. This magnificent region is a testament to the profound influence of supernovae. The shock waves from nearby supernovae have shaped these towering columns of gas and dust, creating dense pockets that may one day form new stars. As these pockets collapse under their own gravity, the energy released will ignite nuclear fusion, giving birth to new suns that will light up the night sky for eons to come. The interplay between supernovae and star formation exemplifies the cyclical nature of the cosmos, where destruction fosters creation. Dr. Neil deGrasse Tyson eloquently described this cycle when he stated, "The universe is under no obligation to make sense to you. In this vast expanse, the seemingly chaotic processes of supernovae and star formation serve a purpose far greater than we often comprehend." To fully appreciate the significance of supernovae as catalysts for star formation, one must consider the broader context of stellar evolution. Stars are born, live out their lives, and ultimately die, enriching the universe with elements that are essential for the formation of planets and, eventually, life. Each supernova marks the end of a stellar life cycle, yet it also serves as a vital component in the ongoing saga of the universe. As we explore these cosmic phenomena, it becomes clear that the interactions of supernovae with molecular clouds create a nurturing environment for new stars. The echoes of these explosive events resonate through the cosmos, shaping the very structure of our galaxy. They remind us of the delicate balance of forces at play, a reminder that in the grand scheme of things, the universe is constantly in flux, and from the ashes of one star, new light can emerge. Imagine standing beneath a vast starry sky, each twinkling point of light representing a sun, a world, or even a distant supernova remnant. Each of these stars has its own story, its own birth, and its own death. The very process that leads to their formation is a testament to the interconnectedness of all things in the universe. Supernovae act as both destroyers and creators, sculpting the cosmic landscape and breathing life into the void. As researchers continue to investigate the relationship between supernovae and star formation, they uncover new insights into the processes that govern the universe. The study of these phenomena not only enhances our understanding of cosmic evolution, but also invites us to ponder our place within this grand tapestry. How do we fit into this cycle of creation and destruction? What can we learn from the stars that once shone brightly before their explosive finales? In this cosmic narrative, supernovae emerge as pivotal players, their shock waves echoing through the cosmos, initiating processes that can lead to the birth of new stars. The beauty of this relationship lies in its complexity and its simplicity, a cosmic dance of energy and matter, forever intertwined. The universe, in all its vastness, reminds us that even in the face of destruction, there is always the promise of renewal. The aftermath of a supernova does not merely signify destruction, it is a pivotal moment that sets the stage for new beginnings. As the shockwaves spread outward, they interact with the surrounding interstellar medium, sculpting it into structures that can foster the genesis of new stars. These waves can compress gas and dust, forming regions of increased density, crucial for star formation. The rhythmic pulse of these shockwaves creates a symphony of cosmic interaction, echoing through the void and awakening dormant regions of space. Imagine a molecular cloud, initially quiet, suddenly stirred by the energetic waves. As the shock front collides with the cloud's material, it squeezes the gas, raising its temperature and pressure. In this moment, a delicate dance of forces occurs. The gravitational pull of the denser regions begins to dominate, capturing surrounding material in a gravitational embrace. Here, the seeds of stars are sown, waiting for the right conditions to flourish. This process is not instantaneous. It requires time and the perfect alignment of circumstances to truly take root. Astrophysicists recognize that the environmental conditions at the time of a supernova explosion are critical in determining whether nearby clouds will form new stars. Factors such as the density of the molecular cloud, its temperature, and the distance from the supernova explosion all play a role in shaping the outcomes. It's a cosmic game of chance and timing, where each variable can tip the scales toward creation or silence. In studying the complex interactions between supernovae and their surroundings, scientists have turned their attention to specific remnants that serve as laboratories for observing star formation. One such example is the remnant of the supernova known as Cassiopeia A. This vibrant nebula, rich in heavy elements produced during the explosion, is a site of intense study. Within its boundaries, astronomers have identified dense knots of material that are collapsing under gravity, giving rise to new stars. The remnants of Cassiopeia A illustrate the profound influence of supernovae on their environments, as the remnants continue to mold the cosmic landscape long after the initial explosion. Another fascinating case is the interaction of supernova remnants with regions like the Orion Molecular Cloud Complex. This vast area, teeming with gas and dust, is a cradle for stellar birth. The shock waves from nearby supernovae have been shown to compress portions of this cloud, stimulating the formation of new stars. Within this complex, several new stars are currently in the throes of formation, illuminating the darkness with their nascent light. The interplay between the remnants of past stellar explosions and the dense clouds of gas serves as a testament to the intricate balance of destruction and creation that defines our universe. As we reflect on these processes, we might ponder the ages of the stars that flicker in the night sky. Each one has a history, a lineage that can often be traced back to the explosive deaths of their predecessors. The cycle of life and death among stars is a grand narrative woven into the fabric of the cosmos. The remnants of supernovae, in their chaotic beauty, serve as both a reminder of mortality and a beacon of hope for new life. The conditions necessary for star formation are not just a matter of physical proximity to a supernova. The timing of these events is also crucial. A supernova may trigger star formation in a cloud that is already on the verge of collapse. But if the shock wave arrives too late or too early, the potential may never be realized. This delicate balance raises intriguing questions about the predictability of star formation. How can we determine which supernovae will be the harbingers of new stars? The answers lie within the intricate modeling and observational studies conducted by astrobiologists and astrophysicists. As researchers delve deeper into these mysteries, they often employ computer simulations to model the interactions between supernovae and molecular clouds. These simulations allow scientists to visualize the complex dynamics at play, providing insights into how shock waves propagate and interact with the surrounding medium. By adjusting variables such as density and temperature, researchers can observe the conditions conducive to star formation. This combination of observational data and simulation reveals a cosmic dance of forces that is both beautiful and complex. The rich tapestry of star formation and supernova remnants exemplifies the interconnectedness of the universe. Each supernova serves as a catalyst, igniting regions of potential that may have remained dormant for eons. This cycle of creation is not merely a scientific curiosity. It speaks to the very nature of existence. As Carl Sagan profoundly noted, we are made of star stuff. The elements that compose our bodies once resided in the cores of ancient stars that exploded long before our time. This realization brings a sense of wonder and humility, reminding us that we are intimately linked to the cosmos. As we continue to explore the relationship between supernovae and star formation, we find an endless well of knowledge waiting to be tapped. Each discovery adds a brushstroke to the grand picture of cosmic evolution, revealing more about the processes that govern our universe. The remnants of supernovae do not simply mark the end, they signal the beginning of new cycles, perpetuating the tale of the cosmos. With each revelation, we are drawn further into this narrative, one that echoes through the corridors of time and space. The universe is a place of profound beauty and intricate complexity, where every explosion paves the way for new creation. The study of supernovae as catalysts for star formation invites us to consider not just the mechanics of celestial phenomena, but the deeper implications of our own existence within this vast, ever-evolving playground of stars. As we gaze up at the night sky, we are reminded that we too are part of this grand story, a narrative woven from the light of countless stars, each one a testament to the cycles of death and rebirth that define our universe. What stories will the next generation of stars tell? What wonders await us in the cosmic expanse? The answers lie in the mysteries yet to be uncovered, in the embrace of the cosmos that invites us to explore, to wonder, and to dream. Chapter 4: Supernovae and Galaxy Evolution. In the cosmic arena where stars are born and die, supernovae stand as monumental events that shape not only their immediate surroundings, but also the grand structure of galaxies. The aftermath of these brilliant explosions contributes significantly to the morphology of galaxies, influencing their shapes and structures in profound ways. Imagine a galaxy as a living entity, its form sculpted by the forces at play within it. Supernovae, with their explosive energy, act as both artists and architects, carving out regions of space and reshaping the stellar landscape. As supernovae erupt, they release vast quantities of energy and matter into the interstellar medium. This ejected material, rich in heavy elements, spreads out across the galaxy, enriching the gas and dust that compose it. Over time, this process contributes to the formation of new stars and stellar clusters, which can alter the galaxy's overall appearance. Think of these newly formed stars as bright points of light, illuminating the dark expanses of space, each representing a new chapter in the galaxy's ongoing story. The feedback mechanism inherent in galaxy formation highlights the interconnectedness of supernovae and the evolution of galaxies. When a supernova occurs, it expels shock waves that compress surrounding gas clouds, leading to the formation of new stars. This is a cycle of creation and destruction, where the explosive death of one star catalyzes the birth of others. The energy released can trigger a cascade of star formation, igniting a chain reaction that influences the development of the entire galaxy. The feedback mechanism illustrates a delicate balance. While supernovae can foster new stellar birth, they can also regulate the growth of galaxies by expelling gas and heat, preventing excessive star formation. Consider the types of galaxies we observe in the universe. Their shapes and structures, whether spiral, elliptical, or irregular, bear the marks of their historical interactions with supernovae. Spirals, with their elegant arms, often host regions of active star formation, fueled by the remnants of past supernovae. In contrast, elliptical galaxies, typically older and with less star formation activity, reflect a history shaped by fewer but more powerful supernovae events. The relationship between the rate of supernovae and the type of galaxy illustrates the complex interplay of forces at work in the cosmos. Observational evidence underscores this relationship, revealing correlations between supernova rates and galaxy morphology. Astronomers have noted that star-forming galaxies, characterized by their vibrant activity and rich gas reserves, tend to experience higher rates of supernovae. These galaxies are often punctuated by bright young stars, hinting at a recent flurry of stellar births that have been invigorated by prior supernova explosions. On the other hand, the quieter, more sedate elliptical galaxies display lower supernova rates, suggesting that their stellar populations have aged, and that the vigorous cycle of creation has slowed. One prominent figure in the field, a visionary in the study of galaxy evolution, once remarked that understanding the life cycles of stars is akin to understanding the rhythms of the universe itself. This perspective invites us to reflect on how supernovae act as the cosmic metronome, dictating the tempo of star formation and the evolution of galaxies. As we gaze into the depths of space, we can imagine the intricate relationships that bind supernovae to the structures of galaxies. Picture a vibrant, star-filled spiral galaxy, its arms winding gracefully outward, each star within it a testament to the cycles of birth and rebirth initiated by past supernovae. The energy released during these explosions not only serves as a catalyst for new beginnings, but also shapes the very framework of the galaxy, influencing its structure and future development. In our exploration of the cosmos, we find ourselves drawn to the idea of galaxies as dynamic entities, constantly evolving and reshaping themselves through the influence of supernovae. The intricate dance of stellar life and death serves as a reminder of the ever-changing nature of the universe. Each supernova is a fleeting moment in time, yet its impact resonates across eons, contributing to the ongoing saga of galaxy evolution. As we ponder the vastness of space, we can take comfort in the knowledge that the very elements that make up our world were born from the ashes of supernovae. These celestial explosions not only enrich the universe, but also play a pivotal role in shaping the galaxies that harbor the potential for life. The cosmos, with its extraordinary processes, reminds us of the interconnectedness of all things, where the death of one star can give rise to the birth of many. As we continue to unravel the mysteries of supernovae and their influence on galaxy formation, we find ourselves at the cusp of understanding the universe's grand narrative. The celestial connections we observe are not merely the result of random events, but rather the culmination of a complex interplay of forces that shape the cosmos. Each supernova, with its brilliance and energy, contributes to the rich tapestry of galaxy evolution, leaving behind a legacy that echoes through the ages. In the ever-expanding universe, supernovae serve as beacons of transformation, illuminating the pathways of cosmic evolution. The relationships we uncover between supernova rates and galaxy types offer us a glimpse into the mechanisms that govern the formation and structure of galaxies. As we turn our gaze toward the stars, we become aware of the profound impact these explosions have on the universe, forever altering the celestial landscape and paving the way for new generations of stars and galaxies. In this grand cosmic cycle, the stories of supernovae and galaxies intertwine, inviting us to contemplate the beauty and complexity of the universe we inhabit. As we reflect on the role of these stellar explosions in shaping our cosmic home, we can appreciate the intricate mechanisms at play, fostering a greater understanding of the universe's past, present, and future. The legacy of supernovae is not merely one of destruction, but of creation, a testament to the relentless march of cosmic evolution that continues to unfold before our eyes. In the intricate web of cosmic evolution, supernovae play a crucial role in determining the morphology of galaxies. Each explosion not only marks the end of a star's life, but also signals the beginning of new structures and forms within the galaxy. Imagine a vast expanse filled with swirling gases and dust, where the remnants of supernovae serve as seeds for future star formation. The shock waves produced by these violent events compress nearby gas clouds, triggering reactions that lead to the birth of new stars. This cycle demonstrates how the death of one celestial body can give rise to many others, embodying the essence of cosmic renewal. The feedback mechanism in galaxy formation is a complex interplay of forces that shapes the trajectory of a galaxy's evolution. When a supernova occurs, it injects energy and material into the surrounding environment, altering the pressures and densities within molecular clouds. This process is not merely a one-time event, It sets off a chain reaction that can influence the star formation rate for millions of years. The energy released can heat the surrounding gas, pushing it outward and preventing further star formation in certain regions, while simultaneously compressing other areas to foster new stellar births. This delicate balance creates a dynamic landscape, with regions of intense activity coexisting with quieter zones, each reflecting the history of supernova activity within the galaxy. As we consider the relationship between supernova rates and galaxy types, we find a striking correlation that highlights the diversity of galactic structures. Spiral galaxies, with their arms teeming with young, luminous stars, are often characterized by high supernova rates. The continuous cycle of star formation, fueled by the remnants of previous explosions, ensures that these galaxies remain vibrant and active. In contrast, elliptical galaxies, generally older and less dynamic, tend to exhibit lower rates of supernovae. This difference can be attributed to the reduced gas and dust necessary for star formation, illustrating how the evolutionary history of a galaxy shapes its current state. The observational evidence connecting supernovae to galaxy structure is compelling. Astronomers have meticulously cataloged supernova events across various galaxy types, revealing patterns that speak to the underlying mechanisms at work. Star-forming galaxies often show a direct correlation with elevated supernova rates, suggesting that the energy from these explosions contributes to the ongoing cycle of stellar birth. This insight allows us to appreciate the symbiotic relationship between supernova and the galaxies they inhabit. Reflecting on the work of prominent astronomers who have dedicated their lives to understanding these cosmic phenomena, we recognize the depth of knowledge they have brought to the field. The late Carl Sagan once eloquently stated that the cosmos is within us. We are made of star stuff. This profound connection between human existence and the stars underscores the importance of comprehending how supernovae influence our universe. By delving into the life cycles of stars and their explosive endings, we gain insight into the very elements that compose our bodies and our world. As we visualize the cosmos, consider the myriad galaxies scattered across the universe, each with its own unique story shaped by the supernovae that have punctuated its history. Picture a galaxy with bright, sprawling arms, speckled with clusters of young stars, each a product of the energetic feedback from past supernovae. These stellar nurseries are alive with the potential for new life, each star a reminder of the continuous cycle of birth and rebirth. In the grand scheme of galactic evolution, supernovae act as catalysts, influencing not only the structure of galaxies, but also the very fabric of the universe. They enrich the interstellar medium with heavy elements, providing the building blocks necessary for the formation of planets and, ultimately, life. The impact of these explosive events extends far beyond their immediate vicinity. They resonate through space and time, shaping the cosmos in ways we are only beginning to understand. The delicate balance of creation and destruction inherent in supernovae and galaxy formation invites contemplation. How do these forces interact to produce the diverse range of galaxies we observe? The answers lie in the intricate dance of stellar processes, where the remnants of one generation of stars pave the way for the next. This ongoing saga of cosmic evolution highlights the interconnectedness of all things, where the death of a single star can lead to the birth of countless others, echoing through the universe. As we venture further into the exploration of supernovae, we encounter the fascinating relationship between supernova rates and the environments in which they occur. The conditions within a galaxy, such as its mass and gas content, play a pivotal role in determining how often supernovae will occur. Galaxies rich in gas and dust, like spiral galaxies, foster environments ripe for stellar birth, leading to frequent supernova events. Conversely, in more gas-poor environments, the cycle slows and the rates of supernovae diminish. Imagine the interplay of forces at work within a galaxy, each contributing to its unique characteristics. The cosmic ballet of star formation, supernovae, and galactic evolution creates a rich and ever-changing landscape. The remnants of supernova explosions not only enrich the interstellar medium but also influence the trajectories of future star formation. The echoes of these celestial events resonate long after the light of the explosion has faded, shaping the stars and structures that will emerge in the eons to come. The observational evidence supporting these ideas is vast and compelling. Telescopes have captured the fleeting brilliance of supernovae in various galaxies, allowing astronomers to analyze their frequencies and distributions. By correlating this data with the structural characteristics of galaxies, scientists are piecing together the intricate puzzle of cosmic evolution. Each supernova is a snapshot in the timeline of a galaxy, marking a specific moment of transformation and renewal. As we contemplate the profound implications of supernovae on galaxy evolution, we are reminded of the beauty and complexity of the universe. These stellar explosions serve as both the end of one chapter and the beginning of another, a continuous cycle that reflects the dynamic nature of cosmic life. The more we understand about supernovae and their role in the fabric of the universe, the clearer our picture becomes of the interconnected web of existence that binds us all. Chapter 5. Supernovae's Influence on Galactic Dynamics. In the vast expanse of the universe, a single supernova can unleash energy equivalent to that of an entire galaxy. This immense release of energy profoundly affects the gas dynamics within galaxies, reshaping the very fabric of the interstellar medium. When a star explodes, it sends shock waves rippling through the surrounding gas, creating a cascade of interactions that influence the behavior of the matter around it. Imagine the aftermath of such an explosion, where the remnants of a star scatter across the cosmos, enriching the environment with heavy elements while simultaneously stirring the gas clouds that linger nearby. As the shock waves emanate from a supernova, they compress the interstellar gas, igniting turbulence and promoting the movement of material throughout the galaxy. This energy input drives the formation of galactic winds, which can sweep through the galaxy like a cosmic breeze. These winds, propelled by the combined effects of multiple supernovae, carry with them a mixture of stellar remnants and newly synthesized elements, forming a bridge between the explosive death of one star and the potential birth of new ones. Galactic winds can extend far beyond the immediate vicinity of the supernova, creating a dynamic environment where matter is continuously recycled. Picture a grand cycle of creation and destruction, where the remnants of a star once bright and full of life become the seeds for new stars and planets. As these winds travel outward, they can carry elements like carbon and oxygen to regions where new stars are forming, enriching the molecular clouds and providing the building blocks for future generations of stellar bodies. Moreover, the influence of supernovae extends to regulating star formation rates within galaxies. The energy released during a supernova can either stimulate or suppress the formation of new stars, depending on the conditions present in the interstellar medium. When shock waves compress gas clouds, they can initiate a process known as gravitational collapse, leading to the birth of new stars. In contrast, if the energy input is too intense, it can disperse the gas, inhibiting star formation by preventing the gas from coalescing. This delicate balance illustrates the intricate dance of forces at play within galaxies. Consider the case of the Milky Way, our home galaxy, which has been shaped by countless supernovae throughout its history. Each explosion contributes to the galaxy's evolution, influencing the distribution of stars and gas. Observations have shown that regions of active star formation often coincide with areas where supernova remnants are present, reinforcing the idea that these cosmic events are integral to the life cycle of galaxies. Another striking example can be found in the Large Magellanic Cloud, a satellite galaxy of the Milky Way. This galaxy is home to the Tarantula Nebula, a region teeming with young, massive stars. The powerful winds and shock waves from supernovae in this area have enriched the surrounding gas, creating an environment ripe for new star formation. The Tarantula Nebula serves as a vivid reminder of how supernovae act as catalysts in the stellar nursery, where the remnants of ancient stars fuel the birth of the next generation. Moving beyond individual galaxies, the influence of supernovae can be seen on a grander scale across the universe. In galaxy clusters, supernovae contribute to the thermal balance of the intergalactic medium. The energy released from supernovae plays a crucial role in heating the surrounding gas, affecting the overall dynamics of the cluster. This interplay between supernovae and the intergalactic medium reveals the interconnectedness of cosmic structures, where the death of one star can have far-reaching implications for the entire cluster. The phenomenon of supernova-driven galactic winds can also lead to the expulsion of gas from galaxies, especially in smaller, less massive systems. When a supernova occurs in such a galaxy, the energy can be sufficient to blow away a significant portion of the gas, stripping the galaxy of the material necessary for future star formation. This process can result in a gradual decline in the galaxy's ability to create new stars, ultimately altering its evolutionary path. As we contemplate these forces at work, we might ask ourselves, what does this mean for the future of galaxies? The interplay between supernovae, gas dynamics, and star formation rates suggests that galaxies are not static entities, but instead dynamic systems constantly evolving in response to cosmic events. Each supernova acts as a reminder of the transient nature of existence, shaping the universe in ways we are only beginning to understand. In some instances, the effects of supernovae can lead to the formation of new galactic structures. For example, in interacting galaxies, the shock waves from supernovae can collide with the gas of a neighboring galaxy, triggering bursts of star formation and altering the morphology of both galaxies involved. This phenomenon illustrates the interconnected nature of cosmic evolution, where the fates of individual stars are intertwined with the larger tapestry of galactic dynamics. The Large Hadron Collider, while rooted in particle physics, also mirrors the cosmic drama of supernovae on a smaller scale. As scientists collide particles at nearly the speed of light, they observe phenomena that echo the processes occurring in supernovae. The energy released in these controlled collisions helps to unlock the secrets of the universe, much like the energy unleashed by a supernova enriches the cosmos with new elements and potential. In this context, it is essential to recognize the contributions of remarkable scientists who have dedicated their lives to understanding these phenomena. One such figure is the astrophysicist Robert Kirshner, whose work has greatly advanced our comprehension of supernovae. He famously stated, quote, "Supernovae are the fireworks of the universe," capturing the awe-inspiring nature of these events while emphasizing their role in cosmic evolution. As we marvel at the splendor of supernovae, let us not forget their responsibility in shaping galaxies. They serve not only as celestial spectacles, but as vital agents of change, sculpting the universe in intricate ways. The next time you gaze at the night sky, consider the unseen forces at work, the remnants of stars that once blazed brightly, now influencing the very dynamics of the galaxies that surround us. The universe is a symphony of creation and destruction, where supernovae play a powerful and essential role in the ongoing narrative of cosmic evolution. With each supernova, we witness a transition from one chapter to another, as the remnants of a dying star breathe life into new worlds. The echoes of their explosions ripple through the cosmos, inviting us to ponder the delicate balance between destruction and creation that defines our universe. As we continue to explore the depths of space and time, let us remember the profound impact of these stellar events, guiding us in our quest to understand the intricate workings of the cosmos. The intricate relationship between supernovae and galactic dynamics reveals itself further when we explore the formation of galactic winds. These winds, born from the explosive aftermath of supernovae, carry with them not just remnants of stellar material, but also the essence of the very elements that comprise the universe. Picture these winds as celestial currents, sweeping through the fabric of space, redistributing matter across vast distances. As supernovae occur in clusters, their collective energy can amplify the effects of these galactic winds. The interplay of multiple explosions creates a dynamic environment where pressure builds, eventually leading to the expulsion of gas from the galaxy. Imagine a balloon being filled with air until it can no longer hold its contents. The release of gas creates a powerful outward force. Similarly, when the energy from several supernovae converges, it can strip galaxies of their gas, fundamentally altering their ability to form new stars. Consider the role of galactic winds in regulating star formation rates. When these winds sweep through areas rich in molecular clouds, they can compress the gas, initiating a cycle of star birth. Conversely, if the winds are too strong, they might disperse the material, hindering the formation of new stars. This delicate balance emphasizes the critical role of supernovae as catalysts, not only in the birth of stars, but also in determining their fate within the galaxy. The concept of star formation regulation through supernovae is vividly illustrated by the starburst galaxies, which experience intense periods of star formation. In these galaxies, the energy input from supernovae can trigger cascading effects that lead to rapid star formation. The NGC 253 galaxy, often referred to as the Sculptor Galaxy, provides a striking example of this phenomenon. Its bright central region is a testament to the intense stellar activity fueled by the energy from supernovae, highlighting how such cosmic events can ignite the birth of new stars in a frenzy of creation. Galaxies are not merely passive recipients of the energy from supernovae. They actively respond to these explosions in ways that can reshape their very structure. For instance, when a supernova detonates in a dense region of a galaxy, the shock waves can interact with neighboring gas, potentially sparking new waves of star formation or triggering the collapse of existing structures. This interaction can foster the growth of star clusters, where stars are born in close proximity, creating stellar nurseries that thrive on the energy and materials provided by their explosive predecessors. As we consider the vast diversity of galaxies in the universe, it becomes clear that the influence of supernovae is not uniform. Each galaxy, shaped by its own history of stellar births and deaths, interacts with supernovae in unique ways. The antennae galaxies, two colliding galaxies, offer a fascinating case study. The merging of these two galactic systems has led to an abundance of star formation, heavily influenced by the numerous supernovae that have occurred in the chaos of their interaction. Here, we see how the powerful forces unleashed by supernovae can create new structures and dynamic environments, altering the course of galactic evolution. In understanding the role of supernovae, we can also reflect on the thoughts of the eminent astronomer Carl Sagan, who once remarked that the cosmos is all that is or ever was or ever will be. This profound perspective invites us to consider how supernovae, as part of the cosmic tapestry, contribute to the continuous cycle of creation and destruction. They are not merely points of light in the night sky, but pivotal events that shape the universe in fundamental ways. The energy from supernovae not only enriches the interstellar medium, but also plays a key role in the thermal balance of galaxies. This balance is crucial for maintaining the conditions necessary for star formation. As supernovae inject energy into the surrounding gas, they heat it, influencing the dynamics of the galaxy and its capacity to support new stellar generations. Imagine the delicate interplay of heat and cold, pressure and release, all driven by the death throes of stars that once shone brightly. To grasp the scope of this influence, consider the case of the Virgo cluster, a vast assembly of galaxies that serves as a laboratory for the effects of supernovae on larger scales. The energy expelled by supernovae in this cluster contributes to the heating of the intracluster medium, affecting the overall dynamics and evolution of the cluster. Such observations remind us of the interconnected nature of cosmic structures, where the life cycle of stars, has repercussions that ripple through the fabric of the universe. As we draw closer to the end of this chapter, we might pause to reflect on the duality of supernovae, their capacity for destruction, and their role as architects of new beginnings. The remnants of a supernova become the raw materials for future stars and planets, a cosmic recycling process that emphasizes the intricate balance of life and death in the universe. Each explosion is not an end, but rather a precursor to the birth of new celestial bodies, a testament to the resilience of the cosmos. This profound cycle of creation, shaped by the explosive forces of supernovae, invites us to ponder the wonders of our universe. How do these cosmic events influence the formation of galaxies, the birth of stars, and even the potential for life? As we continue our exploration of supernovae and their impact on galactic dynamics, we are reminded of the beauty and complexity of the cosmos, a dance of energy and matter that invites us to delve deeper into the mysteries of existence. Chapter 6: The Aftermath, Supernova Remnants and Their Impact. As the echoes of a supernova fade into the vastness of space, what remains is a supernova remnant, a complex structure that tells the story of stellar death and rebirth. These remnants, often resembling intricate shells or glowing clouds, are the aftermath of the cataclysmic events that mark the end of a star's life. They are composed of ejected stellar material, shockwaves, and the remnants of the star's core, all interacting in a ballet of cosmic processes. Observing a supernova remnant is like gazing at a cosmic canvas, where the hues of gases and dust blend into mesmerizing patterns, painting a picture of both destruction and creation. Supernova remnants vary in size and shape, influenced by the original star's mass and the surrounding interstellar medium. As they expand, they become increasingly complex, displaying structures such as filaments and knots created by the interaction of shock waves with surrounding gas. The Crab Nebula, one of the most studied remnants, showcases a web of filaments glowing brightly in the spectrum of light. This intricate beauty is not merely aesthetic. It holds vital clues about the processes that govern our universe. These remnants play a crucial role in enriching the intergalactic medium, the vast, nearly empty spaces between galaxies. When a supernova explodes, it releases heavy elements forged in the star's core into this medium. Elements such as carbon, oxygen, and iron, which are essential for life as we know it, are scattered across the cosmos in the wake of these explosions. Imagine the profound impact of these elements, drifting through space, waiting to coalesce into new stars, planets, and even life. The interaction between supernova remnants and the surrounding gas and dust is a dynamic and transformative process. As the shock waves from the explosion travel outward, they compress nearby gas clouds, triggering new waves of star formation. The remnants act like cosmic seeds, planting the ingredients necessary for new stars to ignite. This cycle of birth and death is fundamental to the evolution of galaxies, creating regions of high density where matter can collapse under its own gravity. Consider the implications of this process. When a supernova occurs in a dense region of space, it can lead to the formation of multiple new stars within a relatively short time frame. The energy released by the supernova not only compresses the gas but also heats it, creating a complex interplay of forces that can result in a vibrant new generation of stars. In a way, supernova remnants can be seen as the architects of the future, sculpting the very fabric of galaxies and influencing their evolution. In the long term, the effects of supernova remnants extend far beyond their immediate vicinity. Over millions of years, the heavy elements released into the intergalactic medium contribute to the chemical enrichment of the universe. This process is crucial for the formation of new stars and planetary systems. Without supernovae, the universe would be a far less colorful and diverse place. The contributions of these explosive events are akin to the brushstrokes of a master painter, each one adding depth and complexity to the cosmic masterpiece. Supernova remnants also interact with other stellar phenomena. For instance, they can collide with the winds generated by massive stars, creating shock fronts that further enrich the interstellar medium. This interaction fosters a dynamic environment, where gas and dust are continuously stirred and reconfigured. The remnants act as a catalyst, promoting the ongoing dance of stellar formation and evolution within galaxies. Throughout history, astronomers have marveled at the beauty and complexity of supernova remnants. They serve not only as a reminder of the explosive lives of stars, but also as a testament to the interconnectedness of the cosmos. As Carl Sagan once said, "The cosmos is within us. We are made of star stuff." This profound truth resonates with the knowledge that each supernova remnant carries the legacy of its progenitor star, influencing the very fabric of our universe. Exploring these remnants allows us to glimpse the universe's history and its future. Each remnant is a chapter in the grand narrative of cosmic evolution, offering insights into the processes that shape galaxies and inform our very existence. Imagine standing before a cosmic tapestry, each thread representing a supernova remnant, woven together to tell a story of creation, destruction, and rebirth. As we gaze into the depths of a supernova remnant, we are reminded of the universe's cycles, how death gives way to life, how destruction leads to creation. The remnants linger, glowing softly in the darkness, holding the secrets of their explosive past while nurturing the seeds of a new cosmic generation. They are the silent witnesses to the ongoing saga of the universe, ever-changing yet enduring. In the grand cosmic scheme, supernova remnants are not merely leftovers of stellar explosions. They are vital contributors to the intricate web of galactic evolution. They shape the very structure of galaxies, influencing their dynamics and morphology. The remnants interact with the stellar populations within galaxies, their shockwaves compressing gas and triggering the birth of new stars. This feedback loop ensures that the life cycle of galaxies is a continuous process, where old stars die to give birth to new ones. As we contemplate the long-term effects of supernova remnants, we see their role in establishing the balance of elements throughout the galaxy. The heavy elements created in the fiery hearts of dying stars enrich the gas clouds that will one day become new solar systems. This cycle of enrichment emphasizes the importance of supernovae in the broader context of cosmic evolution, reinforcing the notion that every star's life is intertwined with the destiny of the universe. Moreover, the interactions between supernova remnants and the interstellar medium contribute to the turbulent nature of galaxies. The energy released during a supernova explosion stirs up the surrounding gas, creating turbulence that can drive galactic winds. These winds carry matter across the galaxy, dispersing elements and influencing star formation rates. This complex interplay illustrates how supernova remnants serve as both destroyers and creators, shaping the dynamics of galaxies throughout cosmic time. Consider the potential consequences if supernova were absent from the universe. Without these explosive events, the interstellar medium would lack the heavy elements necessary for the formation of planets and life. The universe would be a far less diverse and vibrant place, with fewer opportunities for the birth of new stars and the emergence of life. The remnants of supernovae are essential to maintaining the delicate balance of the cosmos, ensuring that the cycle of creation continues unabated. As we continue to explore the cosmos, the study of supernova remnants holds the promise of revealing even more wonders. Each remnant is a treasure trove of information, a celestial laboratory where the processes of the universe can be studied and understood. By observing their characteristics and interactions, scientists can piece together the history of star formation and the evolution of galaxies, enriching our understanding of the cosmos. In this endless dance of creation and destruction, supernova remnants remind us of the beauty and complexity of the universe. They are not merely remnants of what once was. They are the harbingers of what is to come, carrying with them the potential for new beginnings in the form of fresh stars and planetary systems. Each remnant is a testament to the cycles of life and death that define the cosmic landscape, inviting us to ponder our place within this grand narrative. As the remnants of a supernova continue to expand and evolve, they engage in a delicate dance with the surrounding interstellar medium. This interaction, complex and layered, leads to a variety of phenomena that can significantly influence the structure and composition of galaxies. Picture a vast, swirling cloud of gas and dust, once calm and undisturbed, now agitated by the shock waves of a distant explosion. The remnants create pressure waves that compress these clouds, causing pockets of gas to collapse and form new stars. These stars, born from the ashes of their predecessors, carry with them the legacy of their explosive origins, incorporating the heavy elements scattered by the supernova. This process can give rise to star clusters, groups of stars that share a common origin. Imagine these clusters as vibrant communities of stars, each a beacon of light in the cosmic ocean. They are born from the same material, enriched by the remnants of supernovae that fuels their formation. As these clusters age, they evolve into something even more remarkable, a new generation of stars that will also meet their end in fiery explosions, perpetuating the cycle of stellar evolution. The interplay between supernova remnants and the interstellar medium also creates regions of turbulence, enhancing the mixing of gases. This turbulence is essential for the process of star formation, as it facilitates the clumping of matter necessary for gravitational collapse. Over time, these regions can develop into stellar nurseries, where new stars ignite amid swirling clouds of gas and dust. Without the catalytic influence of supernova remnants, these areas may remain dormant, their potential unrealized. Moreover, the heavy elements produced in supernova explosions are not simply cast adrift in space, they are foundational to the development of planets, and, ultimately, life itself. The iron and carbon released during these cataclysmic events are crucial components of the matter that will coalesce into terrestrial bodies. Imagine the journey of these elements as they travel across the cosmos, slowly gathering in molecular clouds, where they will eventually coalesce into new planetary systems. Each planet formed from this material carries within it a piece of the universe's history, echoing the explosive deaths of the stars that came before. The long-term effects of supernova remnants extend to the very evolution of galaxies. Over millions of years, as these remnants continue to interact with the interstellar medium, they contribute to the galactic ecosystem, promoting a cycle of star birth and death that shapes the structure and dynamics of galaxies. The energy and materials released by supernovae can trigger the formation of new stars in regions previously devoid of activity, ensuring that the galaxy remains vibrant and dynamic. Consider the implications of this continual process. Without supernovae, galaxies would lack the necessary ingredients for ongoing star formation. The universe would become stagnant, with fewer opportunities for the creation of new celestial bodies. Each supernova serves as a reminder of the interconnectedness of stellar life cycles and the broader cosmic narrative. Throughout history, figures such as Edwin Hubble have illuminated our understanding of galaxies and their evolution. Hubble's observations revealed the vastness of the universe and the myriad galaxies within it, each shaped by the forces of creation and destruction. As he famously stated, equipped with his 5 senses, man explores the universe around him and calls the adventure science. This adventure is greatly enriched by the study of supernova remnants, which reveal the ongoing processes that govern the cosmos. As we delve into the fabric of galaxies, we are reminded that supernova remnants are not merely fleeting remnants of explosive events. They are the architects of the cosmic landscape. They sculpt the environment, influencing the birth of new stars and the formation of galaxies. The remnants reach out into the vastness, their influence felt across billions of years and light years, echoing the ancient history of the universe. In the quiet expanse of space, the remnants glow softly, a testament to the cycles of life and death that define our universe. They stand as monuments to the stars that once burned brightly, reminding us of their role in the grand cosmic story. Each remnant carries with it the weight of its progenitor star's life, a narrative interwoven with the destinies of countless other celestial bodies. As we contemplate the role of supernova remnants in the evolution of galaxies, we find ourselves drawn into a profound realization: we are part of this cosmic cycle. The elements forged in stellar hearts and scattered by supernovae are the very same elements that compose our own bodies. The universe is a continuous cycle of creation and destruction, with supernova remnants serving as the vital links in this extraordinary chain. In the grand narrative of cosmic evolution, supernova remnants embody the essence of transformation. They are not simply the aftermath of a stellar explosion. They are the harbingers of new beginnings, nurturing the next generation of stars and shaping the galaxies that host them. Each remnant is a beacon of hope, illuminating the path to future creation amidst the darkness of space. Chapter 7. Observing supernovae across the universe. As we turn our gaze to the vast universe, we find ourselves equipped with an array of methods and technologies that allow us to observe the spectacular phenomena of supernovae. The beauty of modern astronomy lies in its ability to capture the ephemeral brilliance of these cosmic events, illuminating our understanding of the universe. Telescopes, both on Earth and in space, serve as our eyes, collecting light from distant stars that have met their explosive ends. Ground-based observatories, such as the Keck Observatory in Hawaii, utilize adaptive optics technology to correct for atmospheric distortions, allowing for sharper images of supernovae. Meanwhile, space-based telescopes like the Hubble Space Telescope free themselves from atmospheric interference, providing breathtaking views of supernova remnants and their surrounding galaxies. These instruments can detect light across different wavelengths, from the visible spectrum to infrared and ultraviolet, revealing the complex nature of a supernova's aftermath. Imagine the light from a supernova traveling through the cosmos, carrying with it the story of its creation and destruction. When we detect this light, we are not merely witnessing a flash in the sky. We are observing the very processes that govern the life cycles of stars. Each supernova emits a unique spectrum of light, allowing astronomers to glean information about the elements present, the temperature of the explosion, and even the distance to the host galaxy. Historically, the study of supernovae has been a journey of discovery. The first recorded supernova, known as SN 1054, appeared in the sky in the year that would eventually bear its name. This celestial event was so bright that it could be seen even during the day for several weeks. The remnants of SN 1054 eventually became the Crab Nebula, a stunning object that continues to intrigue astronomers today. Observing its intricate structure reveals how the explosion of a massive star influences its surroundings, scattering elements across space and creating new opportunities for star formation. In the centuries that followed, supernovae continued to capture human imagination and scientific inquiry. In the 17th century, Johannes Kepler observed a new star, which was later classified as a supernova. Kepler described it as the most beautiful star he had ever seen. This event, later known as Kepler's supernova, provided early evidence that the cosmos was not static, but dynamic, constantly evolving. As we witness these historical supernovae, we understand their significant role in shaping our comprehension of cosmology. They do not simply signify the end of a star's life. They provide essential clues about the universe's expansion and the fundamental forces at play. The light from supernovae carries information about the universe's structure and the distribution of matter within it, allowing astronomers to piece together a more complete picture of our cosmic home. The role of supernovae extends even further into the realm of cosmology. They act as distance indicators, crucial for measuring the vast stretches of space that separate us from distant galaxies. Type Ia supernovae, in particular, are invaluable in this regard. Since they explode with a consistent brightness, they serve as standard candles, enabling astronomers to calculate the distance to their host galaxies with remarkable accuracy. Imagine standing on a distant planet, gazing up at a brilliant supernova that has just erupted. By measuring the light it emits, astronomers can determine how far away it is, much like how a lighthouse guides ships to shore. This method of distance measurement has played a pivotal role in our understanding of the universe's expansion, leading to the discovery that this expansion is accelerating, driven by an enigmatic force we now call dark energy. In the grand tapestry of the cosmos, supernovae are not isolated events, but interconnected phenomena that help us understand the universe's evolution. They enrich the interstellar medium with heavy elements, contribute to the formation of new stars, and influence galactic dynamics. Each explosion is a catalyst for change, reshaping the cosmic landscape and providing fertile ground for the birth of new celestial bodies. As we observe supernovae across the universe, we find ourselves not just as passive observers, but as active participants in the unfolding drama of the cosmos. The light from these explosions connects us to the stars, reminding us of our place in this vast expanse. Each observation reveals a new layer of understanding, deepening our appreciation for the intricate processes that govern the universe. The study of supernovae continues to evolve, driven by advancements in technology and the relentless curiosity of astronomers. The advent of survey telescopes, such as the Pan-STARRS and the upcoming Vera C. Rubin Observatory, promises to unveil even more supernovae, expanding our knowledge and offering new insights into cosmic phenomena. As we embrace the wonders of supernovae, we are reminded of the words of the great astronomer Carl Sagan, who said, "The cosmos is all that is, or ever was, or ever will be." In our quest to understand the universe, supernovae serve as beacons of light, illuminating the path toward discovery and understanding. They beckon us to explore the unknown, to delve into the mysteries of existence, and to marvel at the beauty of the cosmos. With each supernova we observe, we are not simply witnessing a destruction, we are witnessing a transformation. The remnants of these stellar explosions continue to influence their surroundings long after the light has faded. As we embrace the echoes of supernovae, we find ourselves contemplating the interconnectedness of all cosmic events, each contributing to the grand narrative of the universe. In this intricate web of cosmic events, supernovae stand as pivotal occurrences that shape not only the stars and galaxies around them, but also our understanding of the universe itself. The journey of observing supernovae is not merely about the explosions, it is about the stories they tell and the mysteries they unveil. Each observation brings us closer to the heart of the cosmos, reminding us of the profound beauty and complexity of the universe in which we reside. As we continue to explore the depths of space, we realize that supernovae are more than just markers in the sky. They are the catalysts of cosmic evolution, the storytellers of stellar death and rebirth. The light from these events carries with it the history of the universe, connecting us to a past that stretches back to the very birth of stars. In our quest for knowledge, we find ourselves drawn to these extraordinary phenomena, eager to unveil the secrets they hold. Supernovae invite us to ponder the nature of existence, the forces that shape the cosmos, and our place within this magnificent universe. With each new discovery, we deepen our appreciation for the wonders that surround us, captivated by the beauty and complexity of the cosmos. As we forge ahead, guided by curiosity and wonder, the study of supernovae promises to reveal even more about the universe's mysteries. The path of discovery is illuminated by the light of these celestial events, urging us to continue our exploration and to embrace the unknown. In the grand scheme of the cosmos, supernovae remain a testament to the power of transformation, a reminder that even in destruction, there is the potential for new beginnings. The journey through the universe is an ongoing adventure, and supernovae are a vital chapter in the story of our existence. Each observation opens a window into the past, offering glimpses of the processes that have shaped the universe over billions of years. As we stand on the precipice of discovery, we are filled with anticipation for what lies ahead. eager to unravel the mysteries that await us in the depths of space. The cosmos is a vast and intricate dance of creation and destruction, and supernovae are its most brilliant performers. With each explosion, they remind us of the transient nature of existence, the beauty of change, and the endless possibilities that lie ahead. As we continue to observe and study these magnificent events, we become part of a legacy that transcends time and space, forever connected to the stars above. The methods and technologies used to observe supernovae are as diverse as the events themselves. Each technique offers a unique perspective, enhancing our understanding of these cosmic phenomena. In recent years, advancements in spectroscopy have allowed astronomers to analyze the light emitted from supernovae in exquisite detail. This technique breaks down light into its constituent colors, revealing the chemical signatures of the elements formed during the explosion. By studying these spectral lines, scientists can determine the composition and velocity of the ejected material, providing insights into the dynamics of the explosion itself. Imagine the thrill of capturing the fleeting moment of a supernova's light, an event that occurred millions of years ago, now reaching our telescopes. Each spectrum is a snapshot of a cosmic story, telling us not only what elements were produced, but also how rapidly they are moving away from the core of the explosion. This information is essential in piecing together the life cycle of stars and understanding the processes that govern their explosive deaths. Historically, supernovae have served as critical milestones in the evolution of astronomical thought. The discovery of supernova remnants and their spectral characteristics has led to groundbreaking revelations about the universe. Consider the work of Fritz Zwicky, who in the early 20th century proposed that supernovae could be used to measure the expansion of the universe. His foresight laid the groundwork for future studies, making it possible to use supernovae as distance markers, an approach that has transformed our understanding of cosmic distances. As we reflect on the significance of historical supernovae, we see how they have woven themselves into the fabric of scientific discovery. The remnants of these explosions, such as the Cassiopeia A supernova remnant, provide crucial evidence of past events, revealing the life cycles of massive stars and the elements they contributed to the universe. The intricate interplay between supernovae and the evolution of galaxies underscores their importance in the grand narrative of cosmic history. Supernovae are not only pivotal in shaping the universe, but also in understanding its fundamental properties. They act as powerful indicators of cosmic distance, particularly type Ia supernovae, which shine with a consistent luminosity. This allows astronomers to calculate distances with remarkable precision. When we observe these stellar explosions, it is as if we are holding a cosmic ruler, measuring the vastness of space and the expansion of the universe itself. Imagine standing at the edge of a vast, dark ocean, where each wave represents a galaxy. Each supernova is a beacon, guiding us through the darkness, illuminating the path ahead. The light from these events carries vital information about the universe's rate of expansion, leading to profound implications about its ultimate fate. The discovery that the universe's expansion is accelerating, propelled by dark energy, reshapes our understanding of reality, challenging us to rethink fundamental questions about existence. As we delve into the role of supernovae as distance indicators, we cannot overlook the profound impact they have on cosmological models. The observations made from these stellar explosions have contributed to the development of the lambda cold dark matter model, a framework that seeks to explain the structure and evolution of the universe. This model underscores the interconnectedness of supernovae with other cosmic phenomena, linking the life cycles of stars to the grander scheme of cosmic evolution. In the intricate web of cosmic events, supernovae are not merely endpoints but rather catalysts for understanding the very nature of the universe. Their remnants serve as laboratories of stellar evolution, where researchers can study the processes that govern star formation and the dynamics of galaxies. The heavy elements produced in these explosions, such as oxygen, carbon, and iron, are the building blocks of planets and life as we know it. Each supernova contributes to the cosmic recycling process, enriching the interstellar medium and setting the stage for future generations of stars. As we observe supernovae across the universe, we find ourselves engaged in a cosmic dialogue. The light from these explosions transcends time and space, connecting us to the distant past and revealing the story of our universe's evolution. In this way, supernovae are not just celestial events, but profound reminders of the ongoing journey of discovery that unites us all. Each new observation deepens our understanding and appreciation for the complexity of the cosmos, urging us to continue our exploration of the unknown. In this ongoing quest, we find ourselves inspired by the words of those who have come before us, scientists who dared to dream and explore the mysteries of the universe. Their insights fuel our curiosity, reminding us that the pursuit of knowledge is a timeless endeavor. The study of supernovae, with its rich history and promising future, invites us to look up at the night sky with wonder, to seek out the stories woven into the fabric of the cosmos, and to embrace the transformative power of these spectacular stellar events. As we navigate the challenges and triumphs of astronomical research, the legacy of supernovae as both a scientific tool and a source of inspiration continues to unfold. With each supernova that lights up the sky, we are reminded of the beauty and fragility of existence, a testament to the dynamic processes that shape the universe. Our exploration of supernovae not only enriches our understanding of the cosmos, but also invites us to reflect on our place within it, urging us to dream bigger and reach further into the depths of space. In a world where science and wonder coexist, supernovae serve as a bridge, connecting us across time and space, illuminating the unknown, and inspiring future generations to gaze at the stars and contemplate the mysteries that await us in the vast expanse of the universe. Chapter 8. Theoretical Models of Supernovae and Galaxy Formation. The theoretical frameworks that explain the role of supernovae in the cosmos are intricate and multifaceted. These models serve as blueprints, guiding our understanding of how these powerful explosions influence the universe at large. Theories have emerged from the need to comprehend the processes that govern these events and their far-reaching implications for galaxy formation and evolution. Central to this understanding is the concept of energy release during a supernova. The immense forces at play not only obliterate the outer layers of a star, but also produce shock waves that propagate through the surrounding interstellar medium. Imagine a pebble dropped into a still pond. The ripples that emanate from that point demonstrate how disturbances can influence a much larger area. Similarly, the shock waves from a supernova compress nearby gas clouds, initiating a cascade of star formation in regions that may have otherwise remained dormant. This feedback loop reveals how supernovae catalyze not only their immediate environment, but also the larger structures of galaxies. Computer simulations have become a valuable tool in exploring these theoretical models. By creating virtual environments that mimic the conditions surrounding supernovae, researchers can visualize and predict the impacts of these cosmic explosions. These simulations allow scientists to experiment with various parameters, such as the mass of the progenitor star, the type of explosion, and the characteristics of the surrounding gas. In this digital cosmos, researchers can observe how a supernova's shock waves interact with molecular clouds, compressing them to initiate new star formation, or how the expelled material enriches the interstellar medium with heavy elements. One of the most famous simulations, known as the starburst model, illustrates how a single supernova can lead to a cascade of star formations. By modeling the energy released during the explosion, researchers have shown that the shock wave can compress the gas in a nearby cloud, triggering the birth of new stars. This process not only contributes to the life cycle of stars, but plays a significant role in the overall evolution of galaxies. However, as we explore these theoretical frameworks, we encounter several challenges in modeling supernovae. The complexity of these events poses significant hurdles for researchers. For instance, accurately accounting for the various physical processes involved, such as nuclear reactions during the explosion, the subsequent radiation emitted, and the interaction of the shock wave with the interstellar medium, is no small feat. Each of these factors can dramatically alter the outcome of the models. Moreover, the diversity of supernova types presents another layer of complexity. Type 1 supernova, with their unique mechanisms of explosion, differ from Type 2 supernova, which result from the core collapse of massive stars. Each type has its own set of characteristics that must be considered in any theoretical framework. This variability can lead to discrepancies in simulation results, making it difficult to arrive at a unified model that encompasses all scenarios. In addition to the inherent complexities of supernovae themselves, the limitations of observational data can complicate the modeling process. Astronomers often rely on historical observations to calibrate their models, but the rarity of supernova events means that data can be sparse. This scarcity can result in uncertainties regarding the parameters used in simulations. How can we refine our models when we lack complete information? This question drives researchers to constantly seek new observational techniques and data sources, expanding their understanding of supernovae and their effects. Future directions in supernova research hold promise as technology advances. With the advent of more sophisticated telescopes and observational methods, such as gravitational wave detection, scientists can glean new insights into these explosive events. Gravitational waves, ripples in spacetime caused by the acceleration of massive objects, provide a new avenue for studying supernovae and their aftermath. Imagine being able to listen to the universe, to hear the echoes of cosmic explosions that have shaped the very fabric of space and time. This new form of observation may offer information about the dynamics of supernovae that traditional telescopes cannot capture. Additionally, research into the role of supernovae in galaxy formation continues to evolve. As scientists delve deeper into the relationship between supernovae and the structures they help create, they uncover the intricate connections between explosive stellar deaths and the formation of complex galactic structures. The interplay of dark matter, gas dynamics, and star formation is a symphony of cosmic proportions, each element contributing to the grand narrative of our universe. Theoretical models of supernovae also extend to examining their potential influence on cosmic evolution over vast timescales. How do these stellar explosions contribute to the life cycle of galaxies? Are the patterns we observe in the distribution of galaxies shaped in part by the energy released during supernovae? By addressing these questions, researchers strive to paint a clearer picture of the universe's history and its ongoing evolution. As we ponder the future of supernova research, it is essential to embrace the collaborative nature of scientific inquiry. The synthesis of knowledge from various disciplines, including astrophysics, nuclear physics, and computational science, will be crucial in refining our theoretical models. By working together, scientists can develop more robust simulations that account for the myriad factors influencing supernovae and their effects on galaxies. In this pursuit of knowledge, we must also remain open to the unexpected. The universe often reveals its secrets in surprising ways, challenging our preconceptions and inviting us to rethink our understanding. As we explore the theoretical models of supernovae and galaxy formation, we find ourselves on a journey that is as much about discovery as it is about comprehension. Each breakthrough, each new observation adds a layer to our understanding of the cosmos, reminding us that the universe is a vast, interconnected web of phenomena, where every explosion carries the promise of new beginnings. In the quiet moments of reflection, as we contemplate the cosmos, we may find ourselves captivated by the beauty of these processes, the interplay of light and matter, the birth and death of stars, and the formation of galaxies are a testament to the dynamic nature of our universe. Just as the remnants of supernovae enrich the interstellar medium, so too does our pursuit of knowledge enrich our understanding of existence itself. As we continue to explore the theoretical models of supernovae and their impact on galaxy formation, we remain committed to unraveling the mysteries of the universe, one discovery at a time. Each step forward is a reminder of the infinite wonders that await us in the vast expanse of space. The journey is ongoing, and with each new revelation, we draw closer to understanding our place in this grand cosmic tapestry. The intricate nature of supernovae models reveals the delicate interplay between theoretical predictions and observational data. As researchers grapple with the complexities of these cosmic explosions, they continually refine their approaches to better encapsulate the myriad factors at play. The challenge lies not only in understanding the immediate aftermath of a supernova, but also in its far-reaching implications over cosmic timescales. The evolving landscape of galaxy formation is one of the most captivating aspects of this inquiry. Consider the broader context of galaxy formation. The energy released during a supernova not only influences local star formation, but also plays a pivotal role in the distribution of matter within galaxies. When a supernova occurs, the shock waves disrupt the delicate balance of gas and dust present in the interstellar medium, leading to a reshuffling of material. This reshuffling can affect the dynamics of entire galaxies, creating regions of increased density that may eventually give rise to new stellar clusters. Each explosion sends shock waves rippling through the fabric of space, a reminder of how interconnected every element of the cosmos is. The role of supernovae in shaping the morphology of galaxies invites us to think about the universe as a living entity, one that evolves through a series of processes both violent and serene. The remnants of supernovae, enriched with heavy elements forged in the heart of these stellar explosions, contribute to the interstellar medium, serving as the building blocks for new stars and planets. This cycle of destruction and creation is a fundamental theme in the narrative of the universe, suggesting that every stellar death brings with it the promise of new life. As we consider the current challenges in modeling these phenomena, we must also recognize the advances that have been made. The integration of observational data with theoretical frameworks has led to the development of more sophisticated simulations. These simulations attempt to account for the myriad variables that influence supernovae and their aftermath. By incorporating high-resolution simulations of gas dynamics, researchers can explore how different supernova types interact with their environments, enhancing our understanding of their diverse impacts. One critical aspect of future research is the exploration of the role of dark matter in galaxy formation. Dark matter, which constitutes a significant portion of the universe's mass, exerts gravitational influences that can affect how galaxies evolve. How might the interplay between supernovae and dark matter shape the structures we observe today? This question opens up new avenues for investigation as scientists seek to unravel the complexities of cosmic evolution. Furthermore, as observational technologies advance, the potential for discovering new supernovae types increases. The search for unusual explosions, those that do not fit neatly into existing classifications, can provide insights into the underlying physics of stellar death. Each new discovery serves as a reminder of the universe's vastness and complexity, challenging our existing frameworks and compelling us to adapt our models accordingly. Imagine the excitement of uncovering a new class of supernovae, one that offers clues to the very nature of stellar evolution. In addition to observational advancements, the field of gravitational wave astronomy presents a new frontier in our understanding of supernovae. The detection of gravitational waves, ripples in space-time caused by the collision or merging of massive objects, has opened up an entirely new way of observing cosmic events. These waves can provide information about the dynamics of supernovae in ways that electromagnetic observations may not fully capture. By listening to the universe's symphony of gravitational waves, researchers can gain insights into the processes that govern stellar explosions and their aftermath. Engaging with these challenges and opportunities requires a collaborative spirit. The synthesis of knowledge from diverse fields, astrophysics, computational science, and observational astronomy, will be essential in refining our understanding of supernovae and their influence on galaxy formation. As scientists share their findings and build upon one another's work, they pave the way for breakthroughs that could reshape our understanding of the cosmos. As we look to the future, the potential for groundbreaking discoveries looms large. The interplay of supernovae with the cosmic environment holds the promise of unlocking the mysteries of galaxy evolution. Each theoretical model, each simulation, and each observation contributes to a deeper understanding of the universe's intricate workings. The journey of discovery is as exhilarating as the cosmos itself, a testament to humanity's quest for knowledge amid the stars. With every step forward, we are reminded of the beauty inherent in this process. The cycles of birth and death, creation and destruction, serve as a poignant reminder of the transient nature of existence. Just as stars are born from the remnants of their predecessors, so too does our understanding of the universe evolve, enriched by each new insight. The cosmos invites us to explore its depths, to reflect on the profound connections that weave through the fabric of space and time. In this ongoing exploration of supernovae and their role in shaping galaxies, we find ourselves witnessing the universe in all its complexity and wonder. Each explosion carries with it the echoes of history, the promise of renewal, and the potential for discovery. As we continue to delve into these theoretical models, we embrace the unknown, eager to uncover the secrets that lie within the stellar tapestry of our universe. Chapter 9. Supernovae in the Context of Cosmic History. In the journey of understanding the universe, supernovae occupy a pivotal role, not merely as spectacular astronomical events, but as significant milestones in the grand narrative of cosmic history. The historical context of supernovae is woven into the very fabric of our universe, serving as markers of time and evolution. Imagine standing on the shores of time, where each wave crashing upon the sand signifies a cataclysmic event that reshapes the landscape of existence. Throughout history, supernovae have been recorded as bright beacons in the night sky, their luminescence captured in ancient texts and folklore. The earliest observations date back to cultures that gazed in wonder at new stars appearing suddenly, only to fade away. For instance, the supernova observed in the constellation Cassiopeia in the year 1000 became a focal point for astronomers, illuminating the skies and igniting curiosity about the nature of these celestial spectacles. What if these ancient observations were not merely the musings of poets and philosophers, but the beginnings of humanity's quest to comprehend the cosmos? As we traverse through time, we uncover the impact of supernovae on the evolution of cosmic structures. When a massive star exhausts its nuclear fuel and succumbs to gravitational collapse, the ensuing explosion does not merely mark its end. It sets into motion a series of transformative events. The energy released during a supernova can compress surrounding gas and dust, leading to the formation of new stars and even entire star clusters. Picture a cosmic nursery, where the remnants of a supernova become the very ingredients for the next generation of stars. This cycle of death and rebirth emphasizes the interconnectedness of the universe, where every ending heralds a new beginning. Supernovae serve as markers of cosmic events and epochs, providing insight into the evolutionary timeline of galaxies. Each explosion carries with it a unique signature, a fingerprint that reflects the conditions under which it occurred. For instance, Type Ia supernovae, resulting from the thermonuclear explosion of white dwarfs, present a consistent luminosity that enables astronomers to use them as standard candles, measuring vast distances across the universe. This capability extends our understanding of cosmic expansion and the rate at which the universe is stretching. Imagine the vastness of space, each supernova illuminating the path to understanding how our universe has evolved over billions of years. The influence of supernova extends beyond the immediate vicinity of their explosions. The shockwaves generated can induce turbulence in the interstellar medium, promoting the formation of molecular clouds that may give rise to new stars. This interaction is critical in the context of galactic dynamics. As supernovae enrich the surrounding environment with heavy elements and dispersed materials, they contribute to the ongoing cycle of star formation. It is a cosmic feedback loop that underscores the significance of these explosive events in shaping the galaxies they inhabit. Consider the words of renowned astrophysicist Neil deGrasse Tyson, who reminds us of the profound implications of these cosmic explosions. He states, "The universe is under no obligation to make sense to you." Indeed, the complexities of supernovae and their aftermath challenge our understanding, yet they also illuminate the pathways of cosmic evolution. With every supernova, we glean insights into the universe's past, unraveling the mysteries of how galaxies form, evolve, and sometimes collide. Reflecting on the historical context of supernovae, we can learn from the past to inform our understanding of future cosmic evolution. The patterns observed in the life cycles of stars, the processes of nucleosynthesis, and the dynamics of galactic structures all provide a framework for predicting how our universe may continue to evolve. What might the next supernova tell us about the fate of galaxies or the potential for life elsewhere? These questions resonate deeply within the scientific community, driving research and exploration. As we delve into the vast timeline of the universe, we recognize the role of supernovae not just as isolated events, but as integral components of a larger cosmic puzzle. The historical context of these explosions shapes our comprehension of the universe's architecture. Each supernova acts as a witness to the unfolding drama of cosmic history, bridging the past with the future. Through the lens of supernova, we can explore epochs of galactic evolution, tracing the birth and death of stars across time. The remnants left behind are not simply remnants. They are the seeds of future generations of stars, the building blocks of galaxies, and the very elements that will one day foster life. As the universe continues its journey, the echoes of supernovae resonate through time, reminding us of the cyclical nature of existence. Consider the remarkable supernova SN 1987A, which provided unprecedented insights into stellar death and its consequences. Observed in the Large Magellanic Cloud, this explosion allowed astronomers to witness the aftermath of a supernova in real time, illuminating the dynamics of stellar remnants and the processes that govern their evolution. The observations made during this event have shaped our understanding of supernova physics and the role they play in the broader context of cosmic history. As we ponder the implications of these celestial explosions, we are invited to imagine the intricate web of connections that bind the universe together. The heavy elements forged in supernovae enrich the intergalactic medium, fostering the conditions necessary for new stars and planets to form. Each event is a reminder of the fragility and resilience of cosmic structures, illustrating how destruction can lead to creation. Supernovae also provide a critical lens through which we can examine the history of cosmic evolution. By cataloging the frequency and distribution of these explosions, astronomers can piece together a timeline of when and where significant cosmic events occurred. This historical record allows us to trace the evolution of galaxies, revealing how they have changed over billions of years. In the grand scheme of cosmic history, supernovae are not merely endpoints. They are integral to the ongoing narrative of the universe. They serve as catalysts for change, driving the processes that shape the stars and galaxies we observe today. Each supernova is a chapter in the story of the cosmos, a testament to the power of transformation. As we stand at this juncture, reflecting on the influence of supernovae, we are reminded of the cyclical nature of existence. The universe unfolds like a grand symphony, where supernovae play a vital role in composing the melody of cosmic evolution. The echoes of these explosions resonate throughout space and time, guiding us toward a deeper understanding of the universe's past and its potential future. In this context, we learn that the study of supernovae is not merely an academic pursuit. It is a journey into the heart of what it means to exist in this vast cosmos. Through understanding their historical context and their influence on cosmic structures, we gain insight into the profound interconnectedness of all things. What other mysteries might supernova reveal as we continue to explore the cosmic landscape? Each question leads us further into the depths of understanding, where the past informs the present and shapes the future of our universe. The significance of supernovae extends beyond their immediate explosive events, intertwining with the larger narrative of cosmic evolution. These stellar explosions serve as cosmic markers, not just of their own life cycles, but of the epochs that shape galaxies and the universe itself. Imagine each supernova as a time capsule, preserving the conditions of its era, whispering secrets of the universe's past. As we contemplate the influence of supernovae on galactic evolution, we must consider their role in the formation and destruction of cosmic structures. When a supernova occurs, it releases a torrent of energy and heavy elements into the surrounding space. These materials, ejected at staggering velocities, disperse throughout the interstellar medium, enriching it with the building blocks necessary for future star formation. This act of enriching the environment is akin to a gardener scattering seeds across a fertile field, nurturing the growth of new life. One of the most profound impacts of supernovae is their ability to trigger the formation of new stars from previously dormant molecular clouds. As shock waves travel through these clouds, they compress regions of gas and dust, igniting the birth of new stellar systems. Picture a quiet cloud of gas, its potential hidden beneath a calm exterior, suddenly stirred into action by the force of a nearby explosion. This dynamic interaction lays the groundwork for the next generation of stars, illustrating how death can lead to new beginnings. Reflecting on this cycle of creation and destruction, we can draw parallels to the history of our own planet. The heavy elements produced in supernovae, such as iron and nickel, are the very same elements that make up the Earth and, ultimately, all life. This understanding invites us to ponder our own origins and our connection to the universe. Are we not, in a way, the culmination of countless cosmic events, shaped by the explosive deaths of stars long before our own existence? Supernovae also serve as chronological markers within the cosmic timeline, allowing astronomers to trace the history of galaxies. By studying the frequency and distribution of supernovae, scientists can gain insights into periods of intense star formation, the evolution of galaxy clusters, and the impact of these events on the larger cosmic structure. Each supernova provides a unique perspective on the environmental conditions that prevailed at the time, painting a vivid picture of how galaxies have transformed over billions of years. Consider the significance of Type Ia supernovae in this context. These explosions arise from white dwarf stars in binary systems, providing a consistent luminosity that allows astronomers to measure distances across vast expanses of space. They act as cosmic rulers, helping to gauge the scale of the universe and the rate of its expansion. The implications of this research extend beyond mere distance measurement. They inform our understanding of dark energy and the fate of the universe itself. What mysteries might the next explosion reveal about the forces shaping our cosmic destiny? As we delve deeper into the historical context of supernovae, we recognize that their influence is not confined to individual galaxies. The energy released by these explosions can affect the dynamics of entire galaxy clusters, shaping the environment in which they reside. The shock waves can induce turbulence, stirring up gas and dust, and leading to the formation of new structures. Imagine a vibrant cosmic dance, where the remnants of one star's life invigorate the birth of another, creating an intricate balance that defines the cosmos. In contemplating the future of cosmic evolution, we can learn valuable lessons from the past. The study of supernovae offers a glimpse into the processes that govern star formation and galaxy dynamics. By understanding the conditions that lead to these spectacular explosions, we can better predict how galaxies will evolve in the eons to come. How might future supernovae inform our understanding of life beyond Earth? Each explosion carries with it the potential for discovery, urging us to remain curious and engaged in the quest for knowledge. The journey through cosmic history is one of ebb and flow, where supernovae play a critical role in shaping the narrative. They remind us that the universe is not a static entity but a dynamic, ever-evolving tapestry of events that intertwine to create the cosmos we observe today. Each supernova is a chapter in this ongoing story, inviting us to reflect on our place within it. As we ponder the implications of supernovae, we are reminded of the interconnectedness of all things. The history of the universe is a continuum, where each event reverberates through time, influencing everything from the formation of stars to the potential emergence of life. The echoes of these stellar explosions provide a rich source of knowledge, guiding our understanding of the cosmos and our role within it. In the grand tapestry of cosmic history, supernovae illuminate the pathways of evolution, acting as both markers and catalysts. They are not simply events to be observed, but vital components of a larger narrative that encompasses the birth, life, and eventual death of stars and galaxies. As we continue to explore the intricate relationships between these explosions and the universe, we open ourselves to a deeper appreciation of the cosmic drama unfolding around us. What lies beyond the next supernova, waiting to be discovered? The universe is full of potential, and with every cosmic event, we inch closer to unraveling its many mysteries. Chapter 10: Future Research Directions on Supernovae and Galaxies. As we stand at the precipice of astronomical discovery, the horizon is illuminated by emerging technologies that promise to unlock new realms of understanding regarding supernovae and galaxies. Imagine a world where our telescopes can not only observe light but also detect gravitational waves, capturing the silent echoes of cosmic events. The advent of advanced observational techniques and cutting-edge instruments, such as the next generation of space telescopes, is poised to revolutionize our grasp of the universe. Future missions like the James Webb Space Telescope will delve deeper into the cosmos, revealing the intricate details of supernovae and their aftermaths with unprecedented clarity. Consider how adaptive optics in ground-based observatories correct for atmospheric distortions, allowing us to observe celestial phenomena with remarkable precision. These advancements in technology enable astronomers to witness the birth, life, and death of stars in real time, offering a window into the dynamic processes that govern the evolution of galaxies. With enhanced spectroscopy, we will be able to analyze the chemical composition of supernova remnants, unveiling the rich tapestry of elements forged in their explosive deaths. What secrets do these remnants hold about the early universe? Interdisciplinary approaches are crucial in this quest for knowledge. The study of supernovae is no longer confined to the realm of astrophysics alone. It now intersects with fields such as computer science, chemistry, and even biology. By collaborating across disciplines, researchers can develop more comprehensive models that account for the complex interactions between supernovae and their galactic environments. Imagine a team of astrophysicists working alongside data scientists to analyze vast data sets generated by telescopes, unraveling the mysteries of the cosmos through innovative computational techniques. The exchange of ideas and methodologies fosters a more holistic understanding of supernovae, emphasizing the interconnectedness of knowledge. As we look ahead, the role of supernovae in upcoming astronomical surveys cannot be overstated. Large-scale surveys, like the Legacy Survey of Space and Time, will systematically map the sky, capturing the transient nature of supernovae within their grasp. These surveys will enable astronomers to identify new supernovae shortly after their explosions, allowing for immediate follow-up observations across various wavelengths. Imagine the excitement of detecting a supernova in real time, coordinating observations from multiple facilities to study its evolution from the initial explosion to its fading light. Such collaborative efforts will enrich our understanding of the life cycles of stars and their impact on the surrounding galactic environment. Looking at the future, one cannot help but speculate on how supernovae will influence galaxy formation in the coming epochs of cosmic evolution. The feedback mechanisms initiated by these stellar explosions are likely to play an increasingly significant role as galaxies continue to evolve. Supernovae inject energy and heavy elements into the interstellar medium, altering the dynamics of gas clouds and influencing star formation rates. What will be the long-term consequences of these interactions on the structure of galaxies? As massive stars explode, they create shock waves that propagate through their environments, compressing gas and dust and potentially triggering new cycles of star formation. Imagine a galaxy, its spiral arms illuminated by newborn stars, shaped by the echoes of supernovae that occurred eons ago. The remnants of these explosions not only enrich the interstellar medium, but also serve as catalysts for the next generation of stellar nurseries, fostering an ongoing cycle of creation and destruction. In this cosmic ballet, the legacy of each supernova reverberates through time, shaping the very fabric of galaxies and the stars within them. The interconnectedness of supernovae and galaxy formation is a dynamic relationship, one that will undoubtedly evolve as we deepen our understanding of cosmic processes. The future of astrophysics is bright, illuminated by the promise of new discoveries that await us. Each technological advancement, each interdisciplinary collaboration, is a step toward unraveling the mysteries of the universe, inviting us to ponder the profound questions that lie at the heart of existence. What stories will future generations of astronomers tell about the role of supernovae in the grand narrative of galaxies? As we prepare for the next chapter in our exploration of the cosmos, we do so with a sense of wonder and anticipation, eager to uncover the secrets that the universe has yet to reveal. The unfolding narrative of supernovae and their interwoven connection to galaxies presents a canvas for future exploration. As the universe continues to expand, emerging technologies will serve as our guiding lights, illuminating dark corners of knowledge previously shrouded in mystery. One of the most promising advancements on the horizon is the development of next-generation gravitational wave detectors. These instruments will allow us to observe the ripples in space-time caused by the explosive death throes of massive stars. Imagine the thrill of detecting a gravitational wave event from a supernova, offering a new dimension to our understanding of these cosmic phenomena. The ability to measure gravitational waves will not only enhance our comprehension of supernovae, but also provide insights into the formation of black holes and neutron stars. As we gather data from these events, we can begin to piece together a more complete picture of how these remnants influence their surroundings and participate in the cosmic ecosystem. Such discoveries could reshape our understanding of the life cycles of stars and the energetic processes that govern the universe. In parallel, advancements in artificial intelligence and machine learning are redefining how we analyze astronomical data. With vast amounts of information generated by modern telescopes, these technologies can sift through the noise, identifying patterns and anomalies that might otherwise go unnoticed. Picture a sophisticated algorithm trained to recognize the subtle signatures of supernovae amidst the cosmic tapestry. This approach enables astronomers to react swiftly to new discoveries, coordinating observations and follow-ups that deepen our understanding of stellar explosions and their aftermaths. Moreover, interdisciplinary collaboration will continue to be essential in expanding our knowledge of supernovae. The merging of astrophysics with fields such as materials, science, and data analytics opens new avenues for inquiry. For instance, researchers in materials science can study the remnants of supernovae to understand the properties of heavy elements formed during these explosions. How do these elements behave under extreme conditions? What can they tell us about the processes occurring deep within stars? By combining expertise from various disciplines, we can create a more nuanced understanding of the universe's evolution. As we anticipate upcoming astronomical surveys, the role of supernovae as cosmic probes becomes increasingly significant. Projects like the Vera C. Rubin Observatory's Legacy Survey of Space and Time will capture the transient phenomena of the universe, allowing for a comprehensive mapping of supernova occurrences. Imagine a sky where each transient event is cataloged, revealing the birth and death of stars in real time. This wealth of data will not only enhance our understanding of individual supernovae, but also provide insights into their collective impact on galaxy formation and evolution. The influence of supernovae on galaxy dynamics and the interstellar medium cannot be overstated. As supernovae occur, they inject energy and heavy elements into the surrounding gas, influencing star formation rates and the chemical makeup of galaxies. This feedback mechanism is crucial for understanding how galaxies evolve over cosmic timescales. With new observational data, we can refine our models of galaxy formation, examining how the energy from supernovae shapes the structures we see today. Consider the sheer magnitude of this process. Each supernova can trigger a cascade of star formation, igniting new stellar nurseries within the interstellar medium. The remnants of these explosions act as catalysts, compressing gas clouds and enriching them with heavy elements. This interplay creates a vibrant ecosystem where stars are born, live, and die, continually shaping the galaxy structure. As we speculate about the future of galaxy formation, the role of supernovae becomes a central theme. The feedback they provide will likely become even more critical as galaxies continue to merge and evolve. These interactions can lead to bursts of star formation, altering the galaxy's morphology and dynamics. How will the next generation of galaxies look, shaped by the echoes of supernovae long past? The long-term consequences of supernova feedback on galaxy formation present both challenges and opportunities for research. By refining our theoretical models, we can gain insights into the processes that govern galaxy evolution, elucidating how supernova contribute to the cosmic web's architecture. Imagine a future where simulations accurately predict the formation of new galactic structures based on the history of supernovae in their vicinity. The exploration of supernovae doesn't merely deepen our scientific understanding, it invites us to reflect on our place within the universe. Each discovery leads us closer to answering fundamental questions about existence and the nature of cosmic processes. What stories will future astronomers uncover as they sift through the remnants of supernovae, piecing together the history of stars and galaxies? As we embrace the unfolding future of astronomical research, we stand on the shoulders of giants, inspired by the legacy of those who have come before us. The journey of discovery is both humbling and exhilarating, a reminder of how much there is yet to learn. Through the lens of supernovae, we catch glimpses of the universe's grand narrative, urging us to continue our quest for understanding. Just as the light from these stellar explosions travels across eons to reach us, so too does the pursuit of knowledge transcend time, carrying with it the hopes and dreams of generations. What revelations await us as we peer deeper into the cosmos and uncover the secrets held by supernovae and their role in the grand dance of galaxies? As we continue to explore the cosmos, the symbiotic relationship between supernovae and galaxy formation becomes ever more evident. The intricate feedback loop initiated by these stellar explosions shapes not only individual stars but entire galactic ecosystems. Picture a galaxy as a living organism, constantly adapting and evolving through cycles of birth and death. Supernovae act as both catalysts and sculptors, influencing the dynamics of star formation and the distribution of elements across the galactic landscape. Emerging astronomical surveys will undoubtedly deepen our understanding of this relationship. With advancements in technology, astronomers will be able to track supernovae with remarkable precision, capturing their light across a spectrum of wavelengths. This capability allows researchers to piece together the life stories of stars, revealing connections between supernovae and the galaxies housing them. As the next generation of observatories comes online, the data collected will enhance our models, allowing for a more nuanced understanding of how supernovae influence the evolution of galaxies. Imagine a future where every newly discovered supernova is not just an isolated event, but a key to unlocking the history of its galaxy. The insights gleaned from these observations will illuminate how supernovae contribute to the galactic cycle of matter, enriching the interstellar medium and fostering new generations of stars. The feedback from these explosive events can drive gas inflows and outflows, altering star formation rates and changing the very structure of galaxies over time. Moreover, the potential for interdisciplinary approaches cannot be understated. The integration of astrophysics with computational modeling, chemistry, and even social sciences opens new pathways for inquiry. Researchers can simulate various scenarios of star formation and galaxy evolution, testing how different variables interact in the cosmic dance. Such models not only allow us to explore historical phenomena, but also to make predictions about future cosmic events. How might a supernova's feedback shape the next generation of stars and emerging galaxy? As we consider the future role of supernovae, it is essential to acknowledge the ongoing contributions of astronomers and scientists dedicated to this field. Their passion fuels the quest for knowledge, pushing the boundaries of what we understand about the cosmos. With each advancement, we inch closer to answering profound questions about our universe. What patterns will emerge as we analyze the interactions between supernovae and their host galaxies? What new elements will we discover? And how will they inform our understanding of the fundamental processes that govern stellar life cycles? In this ever-expanding field of research, the future remains bright and full of possibilities. The interplay between supernovae and galaxy formation is a dynamic narrative, one that reflects the ongoing evolution of the universe itself. As we harness the power of new technologies and embrace collaborative approaches, the mysteries of supernovae will continue to unfold, revealing the intricate connections that bind stars, galaxies, and the very essence of existence. What wonders await us as we journey deeper into the cosmos, unraveling the stories written in the stars?